Hello, today we're going to talk about relative frequency. This is still a continuation of our topic on probability, and is essentially probability in practice. The goals of our lesson for today is to correctly explain the meaning of relative frequency and correctly calculate the relative frequency of an experimental or the experimental probability of an event. Now, we usually look at probability using familiar materials like dice or coins. So suppose you toss a coin many times and you count the number of times it lands with heads showing, okay? So obviously, as you do it several times, you need to write down the results that you're getting. So you might end up with like heads, heads, tails, heads, tails, heads, tails, heads, tails, tails, heads. Okay, so suppose you threw it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 times. So 12 trials. Okay, so you know from our previous studies that the probability of a coin toss, okay, landing on a head, okay, once of your obviously when you throw it once, is 1/2. So probability of landing on a head obviously is 1 out of 2 because you have one chance of getting a head out of 2 results, and that would be the same for tails. You know that you have 50% chance of getting a tail when you toss a coin once. But suppose you're doing it 12 times, okay? Obviously, you're not gonna get equal results for heads or tails. It depends on how many times you threw you toss the coin. So in this case, suppose this is randomly generated results. Obviously, okay, I have 1, 2, 3, 4, 5, 6, 7. I have 7 out of the 12 trials resulting to heads, and then 1, 2, 3, 4, 5. Obviously, tails 5 out of 12. Okay, and as you can see, this is not equal to 1/2 each. Okay, so this number here, is what we call a relative frequency. It's based on the experiment that we're doing because we're throwing coins, we're tossing coins, and we did it 12 times. Now, if we do it enough number of times, we would be closer and closer to the probability of getting heads or tails for a single toss of single coin toss. Okay, so the value of number of heads divided by the number of tosses, okay, or the value of number of tails that I get divided by the number of tosses is called the experimental probability. So we call this the experimental probability. Okay, as the number of trials or experiments increases, the value of the experimental probability gets closer to the theoretical probability, in this case 1/2 again. So as you do more trials, you get closer and closer to the theoretical probability of getting a head or a tail. Experimental probability is also known as relative frequency, and the definition is shown here. So the relative frequency of an event is defined as the number of times that the event occurs during experimental trials divided by the total number of trials conducted. So if I'm going to write that in formula, I'm going to use a different color. I can say relative frequency is equal to frequency of the outcome or event. So obviously you need to have data for this divided by the total number of trials. And so there's going to be a lot of tallying and counting in this topic. Okay, feel free to pause the video so you can write down notes. Let's look at an example here. So the frequency table here shows the speed of 160 vehicles that pass a radar speed check on a fast road. So we have the speed in kilometers per hour, okay, on the first row, and then we have the frequency. So these are the different speeds of the cars, okay, and we have here the number of cars that registered that speed, okay. So we have here several outcomes and several trials or data. So what is the experimental probability that a car is traveling faster than 70 kilometers per hour? So we look at how many times we measured a car to be traveling at 70 plus, and we see on the table that it's 8. Okay, so again, relative frequency or experimental probability, remember they're the same, okay, equals number of the frequency of the outcome that you're looking at, so you know that there's 8, okay, out of the total trials or total experiments that you did, okay, and in this case it will be divided by 160. So if you add all of these numbers, so you measured it 160 times, so it's 8 over 160, and that is equal to 100 and 1 over 20. So 8 over 160 is 1 over 20, and so that is our experimental probability, okay. That's not really the probability of a car, depending on the number of cars, okay, that you'll get 1. If you have 20 cars, you always get one of them becoming 8. This is only the case within the context of the experiment that you did. If there is a called like theoretical probability, because you know the specific number of cars and specific speeds that they travel to, then you would have this relative frequency closer and closer to that theoretical probability as you collect more data, okay. But in this case, let's accept it as 1 out of 20. So within this experiment, if you have 20 cars, you would expect one of them to be traveling at 70 plus kilometers per hour, okay. Now that idea is related to the next question. Now, if suppose 500 vehicles pass the speed check, now estimate, that's why it's an estimate, okay? How many will be traveling faster than 70 kilometers per hour, okay? And so we use our experimental probability or our relative frequency to estimate. So if we have 500 vehicles traveling, so how many of those will be traveling at 70 plus? And so we know that if we have 500, okay, let's just get 1 out of 20 of that. So we just multiply that by 1 over 20, or 500 divided by 20, and we will get 25 vehicles. And so we say that since the experimental probability of measuring a vehicle to have a speed of 70 plus kilometers per hour is 1 over 20, if there are 500 vehicles, I would expect 25 of them to be traveling at 70 kilometers per hour. Okay, and again, that's an estimate because that is based on the relative frequency based on the data you collected. So in essence, if you want your relative frequency to be closer and closer to your theoretical probability, or to always, so you end up being able to predict, okay, you have to collect more data. And that is how they do it in polls or in like companies that try to predict what's going to happen to the market, or how people are going to react to a certain change in their product, or what products will be in demand. They look at data and try to collect as many samples as possible so that their calculated relative frequency is hopefully closer to the theoretical probability. Feel free to pause the video so you can copy notes. Now let's look at an example next. So this one is a dice, okay? So Kevin rolls a dice of 30 times, okay? And these are the results. Complete the relative frequency table. Now you have to be careful because this is the number of on the dice, so that's the result, okay? The actual result. And then it's asking for the relative frequency, so that's already the how many times one appeared divided by the total number, okay, of rolls, okay, and we say that's 30. So all of these numbers in the relative frequency will be over 30, Okay, and if we count that, we just have 1 out of 30. 2 will give us, how many 2's do we have here? 1, 2, 3, 4. That's 4 over 30. So that's going to be 2 over 15. 3, let's see, 1, 2, 3, 4. Did I miss anything? 5, okay. So 5 out of 30, or in simplified form, that's just 1 over 6. 4 appeared a lot. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 out of 30, so that's 1/3. 5 is the same as 3. Okay, so it's 1 over 6. And then 6 is the same as 1, 2, 3, 4, 1 over 6. Okay, as you can see there, based on what you calculated from the data that you don't have equal probabilities. Okay, so, well, equal experimental probabilities. So you're asked in the next question, do you think the dice is biased? Explain your answer. Now this might be quite confusing. You might think, like, how can a dice be biased? Like, a dice doesn't have emotions. So I thought human beings can be biased. Okay, but in this case, based on the data that you have to judge it based on the relative frequency that you calculated. Doesn't necessarily mean that the dice might actually have an emotion on its own and can choose what number it wants to be to give you. Okay, but based on the data that you have, what do you think is a dice biased? And as you can see here, it is quite biased. Okay, why is that? Because if you roll the dice 3 times, theoretically, okay, you would expect 5 of each, because it's gonna be, so like if it's 6 outcomes, at least 5 of them would be 6, 5 of them will be 5 if it's equally distributed. So you can write that down. When rolling the dice 30 times, you would expect 5 each number. However, that's not the case. So you can see there, the number 1 appeared once out of 30 times. Okay, so you got the number, just shorten that, 1 once, but then you got 10, this one, but got 4 10 times. Okay, so it seems that the dice within this experimental context always lands on a 4, which is quite biased. Okay, right, just that's how you get the full marks for that. Now again, bias means, it doesn't mean that the dice has an emotion and can pick what number it wants to land on. Just in this case, you have not collected enough samples to be close enough to your theoretical probability, or the dice must have been tampered with. Okay, but just based on the data that you have, seems to be biased to 4. Okay, next, Kevin decides to roll the dice 600 times. Okay, calculate the estimate of the number of times the dice will land on 4. Now you have to base that on your experimental data, on your relative frequency. So again, you're rolling it 600 times, and based on your table, your experimental probability or relative frequency for the dice to yield or give you a 4 is 1/3. So you need to get 1/3 of 600. So that's just 600 divided by 3, and you will get 200. Okay, so based on your current data or relative frequency, if you roll it 600 times, you would get the number 4 200 times. Okay, now please make sure you work on your Maths Watch or my iMaths task. Please feel free to pause the video so you can copy, take down notes, make sure you put the date on your notebook, and don't hesitate to send me an email if you have any questions. Thank you.